Welcome back, everybody. So right now we know how to compare the size of sets. We can say this set has more elements than that set via this domination relation. But so far, we don't know that if you're given two different sets, then one has to be larger or let's say equal than the other, right? So that's what we want to prove today, that whenever you have two sets, one they will have to be comparable. Like either they have the same size or one has a size larger than the other one, but it's never the case that they are incomparable. There is no injection from one to the other. This is not a trivial theorem, and actually it requires a heavy use of the axiom of choice, as we're going to see now. The version of the axiom of choice that it needs is called Zorn's lemma. So Zorn's lemma, which we're going to prove when we see ordinals later in the course. So we're not going to prove it for now. It's a kind of a combinatorial version of the axiom of choice that is quite useful in applications, and we're going to use it actually a bunch of times. When you read it, it's a bit technical, so the definition is not hard, the statement is not hard, but it takes a little bit to get the intuition of what's going on. And the best way to get intuition is just to see examples. So we're going to see an example now with comparability of cardinals. So let's start reading the statement of Zorn's lemma. So Zorn's lemma says, so suppose you have a set A. So we're using this calligraphic A to kind of emphasize there is a set of sets. Okay, so imagine A is a collection of sets. Okay, a set of sets. Everything is a set of sets in set theory. So I'm not saying anything but saying a set of sets. But I just want to put the idea in the head that this is a set of sets. Okay, so that's A, and it has this following property. A has the property that whenever you have a subset of A that is a chain, its union belongs to A. So what is a chain? A chain is a collection of sets such that whenever you have two elements inside, one is including the other. Okay? So if you have C and D that are not including each other, this should not belong to a chain. If you have a chain, in a chain, the elements of the chain need to look like all included in the other. Okay, and you never have something like this that is not included in the rest, so it doesn't compare to the rest. So whenever you take two elements, let's say we take the red element here and the black element there, one of them has to be a subset of the other. So if you have a collection of sets like this, it's called a chain. Okay? So the property that we want is that whenever we have a chain, which is a subset of A, so A doesn't need to be a chain. A may have like all kind of sets. But whenever you take a subset that is a chain, the union, which the union in this case is kind of like the bigger sets that we get up here, that's the union of the chain, the biggest one, also belongs to your collection A. Okay, so the collection A is closed and they're taking unions of chains. That's what this is saying. So if you have that property, then you can deduce that A has a maximal element. So what is a maximal element? So maximal element for set A is one that has it's not a subset of any other element of A. So it's maximal and you cannot add any more elements and also get an element of A. So within the collection A, this M is maximal because you cannot make a bigger set that is also belongs to A. There could be many maximal sets because you can have incomparable sets that are maximal and none of them you can increase, but then maybe they are not subsets of each other. So there could be many maximal sets. Zorn's lemma tells you that there exists at least one. How do you use it in practice? Well, in practice, usually every time when you want to prove something using Zorn's lemma, you need to define this collection of sets A, which is going to be particular to your particular application, and then so that what you want is to get a maximal element of A. So you're going to devise A so that if you got a maximal element, then you will get what you want. So essentially, you have to figure it out what collection it is, that if you get a maximal element, then you get what you want. But then to be able to apply Zorn's lemma, this collection must satisfy the property that whenever you have a chain that is a subset of the whole collection, the union also belongs to the collection. Okay? So the proofs are gonna go, you define this collection of set A, you prove that is satisfies the property of being closed under unions of chains, then you use Zorn's lemma to get a maximal element, and then you prove that the maximal element is the object you were looking for. Okay, so all the proofs by Zorn's lemma pretty much go that way. So let's see an example. So we want to show the following, that every two sizes are comparable. So that whenever you have two sets C and D, one is dominated by the other. So one must be bigger than the other, or equal, or they could be equal in size, or one less than or equal to the other. Okay, so let's go with this proof. So from the beginning, let's just start defining what this collection of sets is going to be. So let A be the set of functions f, the set of all the functions that are one-to-one, whose domain is a subset of C and whose range is a subset of D. If I wanted to be formal and use the subset axiom to define this set, you have to notice that functions, remember, are just the graphs, right? So formally a function is its graph. So a function is a relation from C to D. So this is a set that belongs to the power set of C times D, right? It's a relation from C to D, right? So that's the set that we want. Okay, so F is a set of functions, and you say, well, didn't you say that we want a collection of sets, and now we have a collection of functions? Well, a function formally is just its graph, right? So a function is a relation, it's a set of pairs. So we are thinking of these functions as their graphs, so their sets, and so that's why they are sets, because they are sets of pairs, they are relations. So let's start by seeing what it means to have one function included in another as sets. So the observation, you have that a function f is a subset of a function g as graphs if and only if, now let me just write down first the obvious definition, is like for all pairs C, D that belong to F, C, D belongs to G. Right? That's what it means to be a subset. And now if we unravel that, we are saying that for all C that belongs to the domain of F, we have that C also belongs to the domain of G, and F of C, which is D, equals G of C, because C, D belongs to the graph, right? So in other words, this is the same thing as saying that the domain of F is a subset of the domain of G. Every C in the domain of F is in the domain of G, and for all C in the domain of F, F of C equals G of C. Okay, so that's what that means. So another one, we can also say, well, that's exactly the same as saying that the smallest one, F, is the same as the biggest one restricted to the domain of F. Right, so remember this symbol up here means restricted. So we are kind of restricting, G has a bigger domain, and we restrict the domain to a smaller thing, in this case the domain of this one, and on that domain we get the same values. Okay, so that's what it means for a function to be included in another one, that the function is a restriction of the other one, so they are compatible, they always give you the same values, though the biggest one can be defined in more elements, while this one might not be defining those elements, right? So in that sense is that this one is bigger, but wherever this one is defined, they are compatible and give you the same values. So that's what inclusion of functions is when you think of them as sets. Okay, so now we want to make the following observation, that this set A satisfies hypothesis of Zorn's lemma. So let's start from like a easier observation. If B is a chain of functions, meaning that all its elements are functions, then a union of B is a function. If you have a chain of functions B, so it's a collection of functions that are all nested, so they are never incompatible, they are all like included in each other, then the union of B is also a function. Is a function. Okay, so essentially we have, by saying that B only contains functions, they are all relations, they are all the elements are set of pairs. So the union is still going to be a set of pairs, so that's good. So we still have a relation as a union, but then you have to show that it satisfies the property of being a function, okay? So suppose, to show that it is a function, that C comma D belongs to the union of B, and that C comma D prime also belongs to the union of B. Okay? So then you will have, they must belong to some element of this. So there exists an F that belongs to B, such that C comma D belongs to F, right? And then here there exists a G that belongs to B, such that C comma D prime belongs to G. That's what it means to belong to a union. But B is a chain, so that means that whenever you have two elements inside B, they are comparable, right? So either F is included in G or G is included in F, right? So either F included in G or G included in F. But in either case, you will have that F of C equals G of C, right? Because they are comparable. And therefore, notice this one here is D, and this one here is D prime, right? So we started assuming that taking two pairs, C comma D and C comma D prime in the union of B, and then we show that the D and the D prime have to be the same. So that's the property that you want for a function. It's like one thing can never be mapped to two different things. So if one pair is in, the other pair has to give you the same second coordinate. So that's how we get that the union of B is a function. So whenever you have, another observation is that if B is a collection, a chain of one-to-one functions, then the union of B is a one-to-one function. Right, so if B all contains one-to-one functions, is a chain, then their union is going to be a one-to-one function, and the proof is essentially the same as this one, because to prove that something is one-to-one, I have to take C goes to D and C prime goes to D prime, to D, to the same thing. So you have two different things that go to the same, and you want to show that the first things are the same thing, right? But then they're both, proof is essentially the same, because this F and G are one-to-one, so if they both go to the same thing, they have to come back from the same thing. Yeah, so essentially I'll let you guys work out the proof. Very similar to this idea right here. Okay, so, and yeah, by the way, just about the intuition of what it means to have a chain of functions. It means that all the functions there are compatible, right? That's what it means to be comparable. Comparable means the same as compatible, which means that they get the same value. So they are maybe defined on different sets of values, but they always give you the same value. So then when you take the union, they're always, whatever in the domain of the union of the domain, you get the same value. So this is the thing to note. The domain of the union of B, which is a function, is the unions of the domains of the F for F in B. Right, so the union of this whole chain is going to give you a new function whose domain is the union of the previous ones, and the value on each element is determined by whatever function has defined on that domain, and they are all consistent, so it doesn't matter which one you pick. So for an A that belongs to the domain of the union of B, if we take the union of B, which is a function, and we apply this function to little a, we are going to get f of A for any f in B such that A belongs to the domain of F, right? So that means, yeah, so this new function, which is the union, when you apply to a little element A, what you have to do is just take any function in F in the collection B such that the little a belongs to the domain, which we know exists because the domain of this one is the union of these guys, and take f of that one. And we say, well, there are many options. There might be many f's such that A belongs to the domain of F. Well, you always get the same output because of the assumption that B is a chain. So they are compatible. So it doesn't matter which function you choose here so that A belongs to the domain, you always get the same output here. So that's why this function is well defined. Okay, so now we have that the union, here is our A. Let's copy this guy. So remember that we started with this set A that we had up here, that is a collection of one-to-one functions whose domain is a subset of C and your range is a subset of D. And with what we have now, we are in a good moment to show that this satisfies the hypothesis of Zorn's lemma. So if B is a subset of this collection, is a chain, then the union of B is going to be a function. It's one-to-one function by this previous observation, and the domain of the union of B is the unions of the domains of the F's that belong to B, which all of these domains are included in C, and the same is true for the range. We didn't show it, but I'll let you guys work this out. It's also the union of the range of F for F in B, which is a subset of D, because each of those ranges are a subset of D. Okay, so the union of this chain that we took is going to be a one-to-one function whose domain is a subset of C. The range is a subset of D, so we get what we want. So the union of B belongs to A, because it's one-to-one, it's a function, and range and domain are on the right spot. Okay, so that means that we can apply now Zorn's lemma. It satisfies that for every chain the union belongs to it. So here's a set A again. So now by Zorn's lemma, A has a maximal element, which we're going to call F hat. Okay, so since F hat belongs to A, so we know that F hat is a one-to-one function. Domain of F hat is a subset of C, and the range of F hat is a subset of D. So let's see how that looks like. Well, so what we have essentially, so if here is C and here is D, we may have the domains have to be a proper subset. So kind of somewhere here is the domain of F hat, somewhere here is the range of F hat, and then F hat maps that set to that set, right? The blue part to the blue part. That's what F hat is doing. It's mapping one to the other in a one-to-one way, so it's a bijection between these blue parts. This blue part, F hat is a bijection to these blue parts. Okay, but what do we want? Let's go back to what we want. We want to find either a one-to-one embedding from C to D or a one-to-one embedding from D to C. So essentially a bijection from either C to a subset of D or from a subset of C to a whole of D. And here we have a bijection between a subset of C and a subset of D, which is not what we want. But this function, F hat, is maximal, right? So what does it mean? So this is what we claim, that since it's maximal, either its domain is the whole of C or its range is the whole of D. So that's the claim. They cannot be subsets, the proper subsets in both sides. One of the two has to be maximal. And the reason is that if not, this requires a proof, but then I'll just do the picture proof. If not, there will be one element outside and one element outside. And we can make the function bigger by mapping this guy to that guy. It will still be one-to-one because we're picking it outside the range. And we have a larger domain, so we can extend F hat to contain this extra point and this extra definition, and we will have a larger function. And this function will still be in this set A of functions, but then F hat wouldn't be maximal, right? If you could extend it, it wouldn't be maximal. So to be maximal means you cannot extend it, and that means that either you already cover all the domain or you cover all the range, and that's why you cannot extend it in a one-to-one way. Yeah, so that's what it means. So that means so what do we get? So if the domain of F hat equals C, then we have that F hat is an injection from C to D. So C is dominated by D because we have an injection, a one-to-one map from C to D. And if the range of F hat is equal to D, Well, then if you go back, the inverse is going to show that D is dominated by C using F inverse, right? Going back. So either whichever of the two is the whole thing, we have a bijection with the subset of the other, and that's how we get our theorem that any two sets are comparable, and therefore any two cardinals are comparable. See you guys next week.